So we're talking about the TUMs lab, and so we're looking at TUMs, and we've talked about antacids. And before I get started, part of the discussion today will be talking about how we use a strong base. So I've got sodium hydroxide here, okay? And sodium hydroxide is nothing more than a salt that has a hydroxide in it, and it's an arrhenius base, and it's a strong base, group 1 ion, okay? And what I'm going to do is I'm going to put this strong base on a watch glass up here on the document camera. And the reason why I have it there is so that you can see what happens to it over the next 35, 40 minutes. Okay, and a reasoning that we need to do something extra in this lab. So I'm just going to add a few pellets of solid crystals of sodium hydroxide. And if I can actually get them on. All right. All right. But do we have one up there? Can you see it? That's good enough. Oh, I have one there, and I don't want that there. Okay. Okay. So we'll just talk about that one there, and you can see it's a nice round, okay, little pellet of sodium hydroxide exposed to the air. And that'll make more sense as we go through this. All right, so what's the whole point of this lab, the TUMs lab? Well, we're going to use TUMs, which we know is an antacid. You probably have used it before, okay? And where'd my TUMs go? There it is. So we're going to use TUMs. Now, of course, they have different flavors and so forth, but you notice what we're going to do here in this lab is we're going to figure out if, in fact, the active ingredient that they use to help neutralize acid that sometimes backs up from our stomach into our esophagus, right? The esophagus is behind the heart, and if our acidic gastric juice made from the parietal cells that make the HCl backs up to our esophagus, it could, break down the epithelial walls, and we have pain receptors there, and we get something called heartburn, okay, as we talked about. So people will take this. So TUMs is something, this is antacid. It also says calcium supplement. And so if you look at TUMs, okay, it says TUMs, extra strength, 750. Whoa, this grabs your eye. I better buy this. This is extra strength. But I don't know what 750 is, but it sounds like a big number. All right, 750. All right, extra strength. And of course, this one's assorted berries, okay? All right. That's also extra strength, 750. I better buy it. It's going to help me because I've got some, I ate some, tacos in the morning or something. I don't know. Whatever it might have been. Now, of course, this is a different flavor. It doesn't matter, okay? So what is an antacid? Well, as we talked about before, if you remember, we had magnesium hydroxide. And it was what? Insoluble, right? Magnesium being +2, lost 2 electrons. And is very small compared to the other group 2 ions. So it's a weak base because it's insoluble. It looked like milk because it was an insoluble compound. You couldn't see through it. But when I poured hydrochloric acid, if you remember that demo, it got clear. Okay, so this is actually the same idea. So what is the active ingredient? Let's take a look. I love labels. But I look at this and I always laugh. Extra 750, yeah, let's go get it. Okay, so we flip it over. And look at the drug facts. I love the drug, okay? Besides, I love when people say chemicals. This got chemicals in it. And anyone who says that to me, I always say, I hope so. Okay, I hope so. There's chemicals in your food. I hope so. I want some glucose, proteins. Protein's a chemical, all right? I love people like, no chemicals in my food. So what do you gulp vacuums of space, all right? Yes, there are better chemicals that are for you, and there's worse chemicals, okay? This is a drug, oh my God, okay? So these are the drug facts. Whoa, this is, okay, listen, you can't be distributing TUMs on the side here. It's a crazy drug, okay? You don't want people being too basic. Right? Right, it's an antacid. Oh, sorry, I'm here all week. Okay. Now, so what are the drug facts? Let me just zoom in one more time. Okay, if I can do this. Zoom in plus. Okay, if you can see the drug. Look at the active ingredient in this drug. Anyone see that? What is that?
Carbonate.
Calcium carbonate. Yes. You guys did it as a duet. So calcium carbonate is calcium. Carbonate is a polyatomic ion we have seen, and we know it's -2 based on our reference tables. And if you memorize this, calcium is +2, so that's the formula of calcium carbonate. Okay, now it's a solid. We should also know that it's a precipitate, it doesn't dissolve, right? In fact, you should be aware of where it is in our environment. If you've got limestone, if you've got a rock wall in your home that's made of calcium carbonate, you should recognize that seashells are made of calcium carbonate, coral reefs, calcium carbonate. Okay, carbonates proliferate in our environment because it's the way that the earth actually will collect carbon from the air. Okay, it's a scrubber. Okay, our earth can absorb carbon. Scrubber means take something out. So CO2 can be taken out of the air by different things. Okay, by the mountains that makes carbonates, also water. We talked about CO2 hitting the water, and we've talked about already that CO2 is a Lewis acid. Okay, but in this case, we've got ourselves a calcium +2, and it repeats as a crystal lattice of ions. It's an ionic compound. And as we write this, why is this basic? This CO3 -2 can absorb what? We've been writing the Henderson-Hasselbalch. What was my designated conjugate base? What do I keep writing all the time? I would say HA for the conjugate acid. What did I write for the conjugate base? A negative. Well, there's my A negative. This is actually A -2. So carbonate ion can absorb how many protons? 2. Okay. That's an important ratio here. And when it absorbs 2, it makes carbonic acid, but in an acidic solution, carbonic acid breaks down as CO2 and water. Okay? And I'm going to show you that reaction here. So that's the reaction. We know this reaction. Have we ever dropped acid, wait for me to finish before you say yes, in lab? Okay? Remember we had sodium carbonate, washing soda, or you had sodium hydrogen carbonate, right? Which was baking soda, and you dropped acid. Both of them had carbonates in them, and they both fizzed. When we add excess acid onto carbonates, they accept them. It makes them into something called carbonic acid, but then the carbonic acid will decompose into CO2 and water. That's the lava reaction. That's the reaction that came out of my mouth that one time when I had too much acid when I had that issue, okay? The fizzing, the white foam that you see, okay? The baking soda and vinegar reaction, all right? Now, I want to talk about that reaction right now. How does that occur? Okay, so let's say this absorbs 2 H pluses. Okay, I'm going to draw the mechanism for you. Okay, so this is what, and we'll get to this when we get to a different part of the class, but this is the molecular structure of hydrogen carbonate. Now, in truth, the carbonate ion is -2 because it has these 3 lone pairs. It's missing 2 more pluses, right? So this is a -2. It's -1 on this side and -1 on this side. So when I drop acid onto the calcium carbonate, by the way, it's a great antacid because it's a weak base because it's locked in a crystal. When I put it in my throat, the carbonates aren't free enough to grab protons, okay, from the fluid and produce hydroxides and so forth, okay? So it doesn't break down my epithelial cells. So it kind of stays together like magnesium hydroxide does until it hits the acid in wherever the acid might be, if it's in my stomach or if it's refluxing back up my esophagus. When there is H pluses, the H pluses will go into the crystal and they'll, hey, what does an H plus need badly if it's H plus? Does it have any electrons? No, it had 1 electron, it lost it, it becomes H plus. And it needs to have 2 electrons to fill its energy level, so there's 2 there. So the H plus comes here, it's no longer plus, because it gained 2 electrons. And this is something called carbonic acid. H2 CO3. And I told you this can give off an H plus and make the water acidic. Absolutely. Absolutely. It makes our blood acidic. Okay, but if I have an acidic environment, okay, which we do here because in this lab I'm going to add excess H plus. Okay, now what's going to happen is this H plus loves lone pairs. We said Lewis acids, okay, are lone pair acceptors. Lewis bases are what? Lone pair donators. But this is going to come here and protonate this. And what am I adding if I add an H plus? Aren't I really just adding a proton? Okay, so this becomes positive. Now, because we're sitting in water, an H will be ripped off of, I'm sorry. Now, what's going to happen here is that we have water with a lone pair. It's in an aqueous environment that's going to grab one of these H's. And you say, why would one of these H's come off? Well, 3 of these oxygens can kind of make this pair drift. But just believe me right now that it's going to take one of these H's, and this will be H3O plus, as we talked about. But more importantly, this is what happens. Very, very cool. Not something I'm going to test you on, but I don't want to just tell you that carbonic acid in an acidic environment, what? Immediately comes CO2. Watch what happens. Okay? Oxygen is more electronegative than carbon. Oxygen loves electrons. We've talked about that. Coulomically, it attracts electrons more, so it's going to pull this pair. You should know that a bond is a pair. So it pulls this pair back to itself. Hello? What does that become? That becomes water. There's the lone pair that jumped back right there. And a pair is a bond. Makes water. Okay, carbon wants to have 4 valence. So this pair what? Jumps back. And we basically split this right there. And what we make here is CO2. Now, can this reaction be reversed? Can water come into CO2 and make carbonic acid? That's what happens when we breathe. Okay, we've talked about that direction. Here is how we make CO2 and water. Okay, we force water and CO2 to be released and this fizzes out. Okay? All right, good. Now, let's go back to the drug facts, because this is what? TUMs 750. Okay, this stuff is extra strength. So, if we have an acid in our stomach, if it's backing up and causing us problems, we need to neutralize it, yes? With a base. We want to use a weak base because we don't want that strong base to what? Break down our cells and cause a perforated esophagus and internal bleeding. That sounds bad, okay? For everybody, for the company, and more so for you if you do that. So we're not going to chug down sodium hydroxide. Before it gets to your stomach, it's going to start breaking down your epithelial cells, and you'll be internally bleeding, and you'll have probably people yelling at you for doing that. So stay away from the Drano, okay? We don't chug the Drano. You need a weak base. This is a great example. It's locked in this crystal. Only when the H pluses are around does it start acting as a base. But the strong acid is forcing its hand, right? Cool. Now, can anyone see how much the 750 really is per tablet? Milligrams. That 750 is milligrams. It is 750 extra strength milligrams. It's 0.750 grams. Talk about marketing. Just change the unit and it's huge. It is 75000000000. Okay? Picograms. You know, you can change that number just by changing the unit. They didn't give us a unit. Be wary of a number without a unit. So this is 750 milligrams, which is the same thing as saying it's 0.75. It's not even 1. Okay, so someone in marketing says, hey, let's make it a milligram, pump up the number. They're dumb enough to buy it. Believe me, most people probably are. okay? And people probably buy it because, wow, that's a big number. I guess it's got a lot of stuff in it, okay? How tall is Mr. Grodsky? I'm 1 Grodsky. I mean, come on, I'm not that tall. I'm just 1, all right? It depends on the unit, people. Now, so it's an antacid because it's a Bronston-Lowry base. It accepts protons. Now, okay, let's look at other information here, or inactive ingredients. Now, one thing I see here, the inactive ingredient is calcium carbonate. That confuses me, because the calcium carbonate is what does the neutralization, or the carbonate ion. So I don't know why that's there. I guess we can call them up and ask. But what else is in this tablet? Don't think that the 0.75 grams is the 0.75 grams of tablet. Because, does anyone know what calcium carbonate is? Seashells, right? Carbonates, limestone, chalk, chalk. But careful, it's a what? It's a drug. Yeah, little kids. You think they're doing what? Making little hopscotch areas. When you're looking back, hi mom, hi dad. When you turn around, what are they doing? They're sucking on that chalk stick. Yeah, they're taking it down. Because it's a drug. Because their mom fed them too much tacos on Taco Tuesday. All right, all right, I don't know why it's a drug. I don't know. Okay, put the chalk down. Okay, hands up. They're gonna stop us. Throw it out the window. Swallow it. All right, that's kind of weird to me. All right, I don't think of seashells or chalk as a drug, but I guess in this case it is. All right. So could you use seashells? Yes, but you crush them into a powder. It would probably be shards of and cut you. It's better to use the powdered chalk. But has anyone ever had chalk? It's disgusting.
Have you tried it?
Yes, of course I have. I had to because it was a drug. Or it was a chemical. I like chemicals. Okay, now, how do we make this palatable? Oh, what's the first ingredient?
Sucrose.
Sucrose. They add sugar. Okay. They have calcium carbonate. Cornstarch. For anyone who knows that cornstarch is a binder. If you ever add cornstarch to cooking, what's it do? Thickens it up, right? So you want to make sure this tablet what? Sticks together. That breaks apart as chalk. Okay. Talc is this another compound that keeps it dry, so no moisture. We have mineral oil. Artificial flavor. These tablets have to have flavor. Notice I had wintergreen. The one I showed you was a little bit of berry. Okay, so it's sweet. It has a flavor. And notice it has some sodium polyphosphate. There's a reason for that. If you're going to add sugar to a compound, what can inevitably get into the compound? Little microorganisms like sugar?
Yes.
Yes, bacteria. So this sodium polyphosphate, okay, prevents the bacteria growth, okay? So any case, then we have the yellow 5 tartrate and the blue lake. That's just the color. I had wintergreen. What's yellow and blue make? Yellow and blue mixed together makes green. That's how I got the green. Those are food coloring. So there's other things in my tablet. What am I telling you? The first thing we're going to do is take our tablets and we have to crush them to increase the surface area. The calcium carbonate's hiding within the tablet. Okay? We're going to add, why are we going to add excess H+? So that we drive the reaction forward and we find every single carbonate. I can't titrate this like a normal titration because the calcium carbonate is all over the place, yes? I got to crush it, increase the surface area. All right. Watch out for those kids. Take a look. So when they're playing outside with the chalk, when you turn around, okay, they are sucking on that drug. All right. I love how they had the directions. Chew 2 tablets. Okay, what? I didn't know. All right. All right. As directed by a doctor. Doc, what do I do with this chalk? Oh my gosh. All right. Warning labels. Okay. Any case. That is that. So now we're going to design this lab. Now, when I design this lab, I'm designing it around target. What's the point of the lab? The point of the lab is for us to see if, in fact, there is 750 milligrams of calcium carbonate in each tablet. And if we're careful how we set this up and design a lab in our titrations, we should get very, very close. I say that we're accurate plus minus 2 or 3 milligrams to this number. And we'll be surprised about what we get about this. So we're going to be doing the same type of quality control chemistry that they do in labs anywhere besides. Titrations are done everywhere. Calcium carbonate has basic properties. We can use acid-base chemistry to figure out how much per tablet. We're not finding the percent, okay? Let me zoom back because our little guy, who I put it here, zoom minus? Okay, there he is. Hi. Any difference in him yet? No, well, maybe. He's starting to sweat a little bit, I think. He's nervous, okay? It's his first time, okay, on the camera. Okay, now, how are we going to design this lab? We're going to design this lab to figure out exactly how many milligrams of carbonates are this calcium carbonate. By the way, they say calcium carbonate is a great place to get your calcium. I wouldn't be popping TUMs for calcium carbonate, for calcium ions, but any case, you could. I mean, they put that there as a marketing tool because it also has calcium. Hey, it's a good source of calcium. Okay. Any case, so if you need calcium, you can eat chalk, all right? So those kids, they're ODing on their calcium. My bones are too strong, all right? When I jump on my little squares, I break the concrete. Okay, now, so here we go. The first thing we're going to do is, we're going to not just do one tab, we're going to use 2 tabs. Now, I say tabs because I'm edgy. I've learned that if you want to be edgy and cool, which I've never been in my entire life, one easy way is don't say the entire word. I found that out. Someone else told me I could get a tattoo. That was like 10, 15 years ago. Now I need a tattoo on your face to be edgy. I'm not doing that. Don't like needles. But, so we're going to, instead of saying tablets, okay, if you're uncomfortable, I'm saying tabs here. Yeah, okay. So we're going to take 2 tabs. All right? 2 tabs, yeah. That's right. I could drive a motorcycle if I wanted to, but I don't, okay? All right? I think Priuses are cool. Okay, now, so I got to take 2 tabs. Now, how many milligrams of calcium carbonate, target-wise, should there be in 2 tabs if this label is saying what it's supposed to say? 1,500. Yeah, 1,500 milligrams. Let's make that into grams. 1.5. So we should have, if the label is telling the truth, 1.5 grams of calcium carbonate. Just do a little stoich here, okay? So 2 tabs. And in fact, I'm going to write this a little lower because my little friend guy, okay, he's kind of in the way, but I think I need the space. So 2 tabs. And I get a total of what? 1.50 grams of calcium carbonate. Now, I'm going to drop acid onto this to completely annihilate all of the calcium carbonate. It's going to leave us CO2 and water. And that's a really important part of this. The first stop is I'm going to drop acid. But I need to know how much acid should annihilate the target amount of calcium carbonate that's in that tablet. 750, okay? So the first step is you got to go to moles. And I'm going to get rid of, for cool also, we don't write the letter E when you're doing this. I know he told you about that. We're going to get rid of grams. Does anyone know the formula mass of calcium carbonate? If you go to the formula mass or molecular mass parties that we have, we memorize these. This one's always a fun one to do. We always start with this one. So what was it last weekend? Well, no one showed up ever, but we discussed by myself, calcium carbonate's fun. 40 plus 12 plus 16 times 3. Anyone? It's a fun one. We always open up with this one. 100.
I was going to guess that.
Okay, yes. Now you see, Mr. Gradsky, isn't it something different if I use the, to the hundredths place? Yes, I'm rounding, okay? So we get rid of grams and we got moles of calcium carbonate. But I want acid. So watch what I do here. I know some of this might be redundant, but I want to get rid of calcium carbonate. How many carbonate ions in calcium carbonate? 1. And people say that's silly why you're doing that, just to keep track. And I'm going to get rid of calcium carbonate. Now I have moles of the carbonate ion, which, by the way, when I find the moles of the carbonate ion, I know the moles of the calcium carbonate. Okay. But we want to go acid here, H plus. How many H pluses need to be used to neutralize one carbonate ion? Two. That's important. So every one carbonate, I have two H pluses. And that's a really important stoichiometric ratio here, because when we find the moles of H pluses needed for a different part of this lab, we're going to know that we're going to have to do what with that to get the moles of calcium carbonate if we do the reverse. We're going this way, but in our lab we're going to eventually go back this way to find the grams per tablet. Okay, so if I have moles of H plus and there's two of them, going backwards, don't I have to multiply by 2 or divide by 2 to find the moles of the carbonate? Divide by 2. All right, if I'm going this way and I want to get rid of this, won't the H plus be on the bottom, the 2? Yeah, just be aware of that ratio. Okay, and so you notice carbonates go bye-bye, and I got the moles of acid needed to wipe out exactly 1.5 grams or 2 tablets of calcium carbonate, if in fact those 2 tablets were exactly 0.750. I don't know if they are. But do the math. 1.5 divided by 100 times by 2 gives me 0.03. We'll do 0 moles of H plus. I've done this for 2 periods straight, so I'm not amazing with the math. Okay. All right. I'm just tall. Now, let's draw a diagram, because there's a lot going on here. Now, I'm going to use different colors. Now, you don't have to, all right? But I wrote that in purple or blue. I can't tell. Purple. Okay. So I'm going to add that I need, okay, 0.03 moles of what? H plus. Now that is going to exactly what? Neutralize all of the carbonate ion if in fact, now this arrow should be exact, okay? So those people out there saying it's not exact, but this would be the equivalence point. The cool part is, why don't I just titrate the tablets? Crush them, add some water, because the carbonate ions are hiding. They're mixed with the cornstarch. They're mixed with the color. All right, we want to add excess acid to drive the reaction to, what's the word? Completion. Oh my gosh, acid-base stoic problems are completion reactions. So I have to add excess to make this work. If you try titrating just a solution, you'll get to the end point, and then boom, it'll get more basic. It'll be weird. So we just want to drive it to completion. Too many errors. We want to add more. And what's that principle? By adding more H plus and this driving forward, what's that principle that makes sure? Oh my gosh, we should have studied. We did! Le Chatelier's principle. We're still talking about it. So we need to add excess. Now this is an arbitrary amount. Remember, you're going to be doing this for another lab. I'm walking you through these steps. I'm making you learn them. Tonight you're running a procedure, part of this. So here is the extra. Okay. Now, I'm adding an extra arrow there. We don't know if our tablets are exactly 750. In fact, I bet they're not. You're going to find out with the very careful Lab Friday, well, maybe Lab Friday. Exactly. So in truth, this is the target area. Our carbonates may be more than 750 or less. So I have to add excess for 2 reasons. To drive the reaction to completion and to give me some wiggle room. What if my what? Amount of carbonate in my tablets is greater than 750. I have to have more enough acid to make sure that I drive that away. Okay? Now, so here's an arbitrary amount. How much excess should I have? I'm going to tell you my thing. I'm going to add 0.01 extra. And therefore I have a total of what? 0.040 moles of H plus I want to add. This is an arbitrary value. It's something that I'm deciding. Could you have decided more? Yes. When you do this very similar lab for the next lab that we do, that you're going to make from scratch, understanding this process first, you come up with that. I'm telling you we're going to add 0.01. Now, how many moles of acid do I have to add? Total. To be in an excess scenario, to drive the reaction to completion and to wipe out extra carbonates if in fact the tablet has more. So I decided the total amount of moles we have to add is 0.04. Okay, let's back up. Let's go over the steps so far. Number one, we're going to crush 2 tabs. For those that aren't cool, those are tablets, okay? Sorry. All right? Now, you're going to crush 2 tabs with a mortar and pestle. Who knows what that is? Who cooks? Yeah, you're going to take basically a hard backing bowl with a little bit of a handle with a flat edge, and you're going to crush the tablets. Why are we crushing the tablets? To increase the surface area so it can expose all the carbonates. We're going to crush the tablet. 2, we're going to add to a 600 milliliter beaker. And we're going to add some distilled water. Do you think the amount of water you add is important? I'm after moles of the carbonate. The answer is no. So you can add, it's got to be distilled because distilled doesn't have any other impurities that could, compete in these reactions. So we'll say 200. And that's not something you have to measure. You can use the markings on the beaker and estimate because it's about the moles in the beaker. This is not about molarity now. We're not trying to find the molarity. We're just saying we want the moles, okay? And then we're going to what? Stir with a magnetic stirrer. So the magnetic stirrer is with a stirring bar is going to be on. And it's going to look, if we're using wintergreen, green, cloudy, goopy, because calcium carbonate, cornstarch, and a lot of things don't dissolve very well. Okay, very important. Now, 4, we're going to heat and add 0.04 what? Moles of H+. And the reason why we're heating, when I drop acid onto the carbonate mixture of sucrose, cornstarch, flavoring, food color, we're going to make CO2. We want it to leave. But don't we know that CO2 can react with water? Carbonated beverages, CO2 loves to react with water. So we heat it with the acid to make sure all the CO2 gets to the surface and leaves. We do not want any CO2 left. CO2 is like the conjugate acid. It's going to disrupt our results. So we're going to heat it so the CO2. If you were to heat a carbonated beverage, what happens to the fizz? You think it's going to stay or is it going to leave faster? Right. A hot day, an open soda is going to go flat faster. Same idea. So we're going to drive the CO2 out. Here's my problem. How do I add 0.4 moles of H+? We can't count. There's 0.1. You can't do it. We're going to have to use a solution, and here you have to design one. I'm going to help you design this. Okay. I got to make a solution. I got to know the molarity of a solution. So guess what? Molarity is equal to moles over liter. Okay. Couple arbitrary values here. I want to deliver how many moles?
0.04.
So that goes here. 0.04. Now the question is, here's an arbitrary value. Do I want to add 1 drop of the solution, and the 1 drop will be 0.04 moles? Would that be a very concentrated acidic solution? How dangerous that would be, and it's hard to know when you get 1 drop, right? So that's not a good idea. Do I want to add 10 liters to a beaker that has 600 milliliters? Well, that would be silly. So I suggest And we can, let's add 100 milliliters. We have to measure it accurately, don't we? Because we have to know our liters times the molarity to get the 0.04, correct? We're kind of working backwards here. That's the difference. I keep doing this to you guys. We keep doing things frontwards and backwards. You're looking at the design of the lab to truly understand the lab. Okay, that's what I'm doing. So, I think it's easy to measure 100 milliliters. I could have picked 50. I could have picked 10. If I used 50, wouldn't the molarity be twice as concentrated? If I used 10, wouldn't it be 10 times concentrated? So I don't want to deal with concentrated acid. So I want to be able to measure a good amount that's easy to measure, 100, and still be dilute enough to be safe to handle. So I arbitrarily picked 100 milliliters. I want you to use 100 milliliters. What's that in liters? This is an arbitrary value. We could have picked a different volume. That would make our what? Solution less or more concentrated. I picked a high enough volume to make the solution be less concentrated and more safe. And something we can actually measure. 100 milliliters, I'll give you a graduated cylinder, and you got to measure that out perfectly out to the 100.0 mark to get to know this number at this point right here. Okay, now, what's the molarity? What's 0.04 moles over point, notice I put this in liters, right? So dividing by 0.1 gives us what? That is our molarity of our solution that I need to make for you guys. See, if I just gave you the lab, you just take 0.4 molar and we just add it, we don't know what we're doing. You came up with this. In your next lab that we do, that you're going to decide, you're going to figure out the arbitrary values that lead you to a safe molarity. All right? All right, so we have our important concentration that we need to make, and I'll talk about probably tomorrow how we make those. We'll do one titration tomorrow for sure. All right, so now we're going to add 100 milliliters of 0.40. Now going backwards, you can figure how many moles, right? Kind of simple, like 0.1 times 0.4 gives you 0.04, right? So we're doing things in the opposite way to design this lab. But the bottom line is, party people, we are now here. Yeah, I found a better red marker. And that wasn't a straight line, and I know Mackenzie's out there saying, okay, come on, guy.
It's more of like the black dash.
Okay, yeah, I know. That's all good. All right. Any case, she's forever in my video. All right. Shout out, Mackenzie. Come on. Come on, girl. Hey, she clapped. Yep. She's actually a seal. Okay. Now, so in any case, we added 0.04 moles of acid. Now, so we're going to change this to number 4 right here. Heat and add 0.04 moles. Well, what are we really adding? We're adding 100 milliliters. You better measure this accurately, okay, of a 0.40 molar hydrochloric acid solution. So I guess in number 4, I should say measure out carefully, or 4A, measure out carefully 100 milliliters of our 0.4 molar HCl. So maybe that's 4A. So I'm saying heat and add 100 milliliters. So we're going to have to actually measure that, so you can fix that at your own time. All right, but we're going to have to take a solution we're going to make, measure, because it's important in titrations that we know our solutions. If this solution that we make, and if I have low confidence in that number that I make, then the whole lab is going to have low confidence. What I mean by that is we're not going to be confident in the number that we get for the milligrams of calcium carbonate if this is a value that we can't trust. We have to be very careful and make exactly 0.04. We'll talk about that more tomorrow. But in any case, by dropping 100 milliliters of 0.4 molar hydrochloric acid solution, we know that we're now at this point. We have shot past the equivalence point, wherever that might be. And again, by being in excess, we've driven the reaction to completion. By heating it, we've taken sure none of the CO2 backs up in the water and stays there, which would be an acid. We're adding more acid than we thought that was there. We're going to drive that away by heat. Everybody with me? Yay, okay, now, we're gonna have to, and this is what we call this procedure, a back titration. Yeah. We're going to titrate the excess back to the equivalence. This is called a back titration. So what we're gonna do is titrate this excess. Now, we don't know. Remember, this line right here is the target, assuming that our two tabs, okay, are 750 apiece. So we have what? Right now, we have a what? Beaker that's got this slurry. We poured in, by the way, we poured in the acid. We didn't titrate it. I'm adding excess. So take your 100 milliliters of your 0.4 molar and carefully add it in. And the stirring rod's gonna stir. And we're gonna heat it to make sure that we drive it all off. We're not titrating, we're just gonna add excess. So we're not like going drop by drop. No, we're just adding excess. Boom. Who's in greatest quantity in this beaker now? Should there be any carbonate ions? If I had a test, like I did last test, and draw me the ions, should there be any CO3 negative 2? No, we shot past the equivalence point, correct? Where am I at this point? Aren't I at a 0.5 value on our curves that we learned? 0.5 problem, remember? What's the final pH? You found out how much excess base or acid. Remember we talked about that? For those that don't have me in class and watching this video, I call 0.5 questions the final pH of a titration that you shoot past the endpoint. But what we're going to do is, we're going to go backwards now. I want to add hydroxides to this beaker. Now, there's no carbonates left. What should I draw in here? What's in excess? H pluses, correct? How much H pluses? Is there 0.04 moles of H pluses in there? No. How much got wiped out? Large amount. Depends upon how much what? Carbonate I have. So party people, what's the target amount of excess I should have? 0.01, assuming the tablets are saying what they're saying, correct? So we want to add hydroxides, and we want to do what? We want to back titrate the excess. Now think with me, what's this going to do? I'm going to figure out how many H pluses. Why did we titrate? Now I'm not trying to find the molarity of the solution like I've been doing. I want to find the moles of this. Ooh! If I can find the moles of this, I know exactly where this arrow stops. Think about it. If I find the moles of H plus to be 0.017, aren't I going to titrate back to like here? If the excess is 0.017, aren't I going to titrate back past that? And doesn't that mean my tablet has less carbonate than we thought? We don't know exactly what it will be. That's our target. That's why we have this what? This buffer area, this unsure area, this wiggle room, as I said before. So we want to titrate the excess H pluses. Guess what? We need a solution. Oh my gosh, we need to figure out the molarity of a base. What base should I use? Don't I want to make sure I find every H plus, so I better use a what? Strong base, okay? Now, I need to know what? What's the target amount of excess? I don't know if it's going to be that, but I have to do what? Design a titration based on that target amount. So how much excess H pluses? How many moles of H pluses should be in here? 0.01. So watch how we do this. Molarity is what? Mole over liter. Ja oder nein? Yes? Good. Now, what should be the moles of base that I drop from the burette? Because now I'm going to titrate carefully. Okay? No. I'm titrating the excess. This is the excess. Fruit Loops. Excess. Okay? So I'm going to try to, the target is 0.01 moles. Oh my gosh, so there I put it. Notice that came from an arbitrary value that we started down this rabbit hole. So this is 0.01 moles, that's the excess. Everybody with me? There should be about something. It could be less or more, but that's the target. These tablets are not going to be twice or half. They're going to be close to that number. TUMS wants to make sure that they don't get sued. Or they don't want to lose money, do they? They don't want to give you more calcium carbonate than it says. Okay? So they're going to be somewhere close. All right? So we got to make sure that we're around there. Now here comes the next arbitrary value. Think about what we're doing here. I poured in acid to get the excess. I could care less, but now I need to know exactly the moles here. So what we're going to do is we're going to have a burette. It's going to have the strong base, sodium hydroxide. Hey, how's our friend doing? Okay. And we're going to drop it onto this what? Slurry of excess H pluses. I want to drop 0.01 moles. Now think with me. This is arbitrary. I've got myself a burette. Now burettes that we use are 50 milliliters. 50 milliliters. Now if you're from North Wading River like I am, we say 50 milliliters. But, so I've got my 50 milliliter burette here in the house, yo. So listen, I've got my 50 milliliter burette. I want to fill this with a sodium hydroxide solution that I'm going to titrate to drop, hopefully, 0.01 moles or something close. But I need to measure exactly how much base because I don't know if it's going to be 0.01. What should my target volume be? Should I make 0.01 with 200 milliliters I have to add? This is a 50, or 50 if you're not understanding, 50 milliliter burette. Should I be filling this 4 times? Would that be smart to do this titration? Think with me. How about I have about halfway somewhere? So if I need more, or if I need less, I've got the what? Wiggle room. Wouldn't be smart to make it 50. What if I need more? Why would I need more? Because the carbonate is, the tablet has more or less, right? So I say, arbitrarily, we should add about 20 milliliters. Let's not make that the target. Let's say 20 milliliters. Why is that good? Because that's somewhere around half of my 50. I'm picking 20 because the math is easier, okay, to do in my head, all right? And my head is way up there, so, you know, I do it for me. So I could pick 25. You could pick anything you want. I wouldn't pick 2. This becomes too concentrated, all right? And I wouldn't pick 200 milliliters because I'm going to fill this back up 4 times. I want to stay within 50, but stay in the middle. It makes sense to be in the middle, so if I need more, I got room for it. If I need less, I got that. So I'll give you 50, but our target should be 20 milliliters. Could we pick 25? Could we pick 15? We're arbitrarily coming to the decision. When you make this lab up, next time it's done in a different lab, but you're designing it, you come up with that. So I'm going to say we're going to arbitrarily make it 20 milliliters. What's it in liters? 0.02. Oh my gosh. 0.01 divided by 0.02. I think that's point what? What's that equal? 0.01, isn't 0.01 half of 0.02? I think. So this is going to be what? 0.50 molar concentration. Of what? NaOH. We just figured out the concentration we have to make. This one up here was, of course, HCl. Now, what's the lab, party people? So, what would be number 5? After we added the excess, make sure we heated, stirred for a while to make sure that we drove off all the CO2. We're going to set up a titration, okay? And we're going to do what? Titrate with 0.5 molar NaOH to the equivalence point. You can use an indicator, drop by drop. You can set up the pH probes and do a graph and see where the equivalence point is. Which one is more of a precise method? Yeah, I would do the pHs and do drop by drop, or do the half, or whatever we gotta do. Okay, you can use the indicator, and that would still work just as well, but it's an approximation. Okay, so I don't care, but think with me. In the last step here, we're gonna titrate with 0.5 molar NaOH. What am I finding? I'm gonna find how many milliliters of NaOH it needs to neutralize the excess. And the moles of NaOH that I get will equal the moles of what? H plus is in there. I'm gonna find this line. Let's pretend this line is 0.02. If I needed 0.02 to work back, if 0.02 moles of acid were needed, you with me? How many were needed to neutralize the excess? If we found the excess to be 0.02 and we added 0.04, how many moles of H pluses were needed to neutralize? 0.02. This line here is what you're looking for. I need a grandiose color. Okay, I don't know if it's grandiose. That is now exactly the moles needed to neutralize the CO3. That moles of what? H plus. Take those moles. Because 2 H pluses, or 2 moles of H pluses are for 1 carbonate, what are you going to do with those moles? Divide by 2. You got the moles of the carbonate. You're going to times by what? 100. You're going to get the grams of carbonate per 2 tablets, so you divide by 2 to get 1 tab. That's the lab. Okay? All right.